Hi, welcome to chapter 2 of Norton's Earth Science. Uh, let's get started on talking about plate tectonics. What we're going to be doing in this lecture is talking about what Alfred Wagner did and his research that led us to understanding this concept of continental drift. We're going to look at the process of seafloor spreading and observations that geologists can use to confirm Alfred Wagner's hypothesis. Uh, we're going to look at the differences between the lithosphere and asthenosphere and look at the major plates associated with uh, these plates. We're going to look at the different types of plate boundaries, and we'll look and you should be able to sketch them by the time we're finished with this lecture, and you should be able to describe the nature of motion associated with these. We're going to look at the different types of plate boundaries and explain why new boundaries can form and how how plates can cease to exist. We're going to look at some of the major ideas associated with modern geology and basically how plate tectonics has evolved from continental drift and how we've modified our hypothesis substantially. We're going to describe some of the measurement techniques. We're going to talk about paleomagnetism. And last but not least, we're going to explain some of the methods used by scientists to calculate the rate of motion. So to talk about plate tectonics, we really need to start talking with kind of the predecessor to plate tectonics and continental drift. And the first person to come up with the idea of continental drift was a gentleman by the name of Alfred Wagner. Now, he's a very interesting man. I don't think he gets as much credit as he possibly maybe should. He is in this earth science book, many different chapters. He was actually not a geologist, as one would kind of think. He actually went to school for meteorology. In fact, he fell in love with his professor's daughter, and his professor was Dr. Koppen, who we now know in our chapter on climate is climate classification systems is named after Alfred Wagner's father-in-law. One of his other contemporaries who he met with extensively and studied with was a gentleman named Milankovitch. You may know this name from Milankovitch cycles, and we'll talk about that in a chapter on glaciers and these Milankovitch cycles. So Alfred Wagner, being a meteorologist, he was looking into the atmosphere, particularly what happens in really cold environments. And so he spent a number of different campaigns traveling across Greenland, looking at these various ice sheets and what happens to air at really cold temperatures. And one of the things, when he was going out, he went on a Arctic expedition, his second great Arctic expedition. He unfortunately, one of the members of his campaign broke his leg, and he fell into a crevasse, which is not uncommon out there. And usually that would have meant he would have ultimately perished. But Alfred Wagner went and rescued Johann Koch, and unfortunately, during this expedition, he took a lot of time to recover. And one of the things when he was recovering, he was laid up in bed, and he noticed the way that the continents. He saw a map of the world and saw that the continents fit together like a jigsaw puzzle. You may have seen this, but it sparked his interest. And one of the things about scientists is you observe the world constantly, and if you see something, try to figure out why that is. That's what earth science is trying to know the world. And so his hype, well, Well, in the middle of his research, unfortunately, World War I broke out. And in World War I, he was commissioned, it was in uh, in in Berlin, in Belgium, excuse me. And as he was a meteorologist for the war, he unfortunately was injured, and so again he was sent home. And while he was at home, he proposed a book and talked about this idea of continental drift. And he was the first person to come up with the term Pangea. If the continents were drifting apart, at one time they would have drifted together. And if they were drifting together, they would have been one supercontinent named Pangea. Now, during this time, as he wasn't a geologist, he was not really taken seriously. And so collecting more data, I'll talk a little bit about his data here in just a second, but he wanted to get more data to substantiate his hypothesis. And in doing so, unfortunately, he was trekking across Greenland again, and he died. And so he did not live to see what any geologist, any introductory earth science or geology book shares his name, but he didn't live to see this. The next geologist that we're going to be talking about, this man was a geologist. His name was Harry Hess. And during World War II, he had access to, he was on a boat, he was with the American Navy. And as a result, he had access to sonar. And he was actually able to use the sonar in his boat to send a sound wave down and determine how far an object was. And so he turned it on its side, and so it shot down instead of shooting out to see what the land shape was, if we could make a great landing, if that was a good spot to park a boat, make a amphibious assault. So he shot the sonar down, and it told us how deep the ocean was in different parts of the ocean. Up until this time, we thought the ocean floor, once you got away from the continent, was exceedingly flat. But he didn't see that. As it turns out, he found out in the middle of every ocean, there's a large high region. Additionally, he found that there are some areas that are real close to the continents, some continents that are really deep. This led to his understanding of this thing called seafloor spreading and subduction. And so by the 1968, we realized that we had to really change Alfred Wegener's hypothesis. We started with the hypothesis, we gathered data, and as we gathered data, we had to modify our hypothesis. And so now the hypothesis was so different from the original data, we wanted to not confuse the two. And so we now have used the term plate tectonics that involves both Alfred Wegener's idea of these continents moving and what's happening on the ocean floor. So Alfred Wegener's hypothesis talked about how these continents fit together. And again, he took a map of the world and cut out the continents, and it more or less fit together to form a supercontinent called Pangea. So he used that, and so then he started looking for additional evidence. One of the other things that he looked at is these different climate belts. We know that right around the equator, we get a lot of rain, and those regions end up having different types of weathered rocks. If we go a little bit further towards about 30 degrees north and south of the equator, we have some giant arid belts. And so we would expect to find those same belts of arid in weathered materials and evidence of these climatic belts in different latitudes. And that's in fact what we found. We also found fossils from different locations. And then also we started looking at the different layers of rocks. And we saw that those layers of rocks do in fact match on one side of one continent to the next. So we could actually use those together. So here's an image of how these continents are fitting together. And you'll notice there's some a little bit of overlap. Well, as it turns out, if we start looking just at the continents, it doesn't fit as well. But if we extend the continents all the way out to the edge of the continental shelf, which is where the continent, right next to the continents, where the rocks change from continent crust to oceanic crust, that the fit is even better. Here's an image looking at these different climate belts of these ancient climates. We'd expect to see in the swamp areas that will lead us to a sedimentary rock called coal. And as it turns out, you can see there's a lot in the United States, but that layer of rock extends all the way across the different continents if we put the continents back together. I mentioned those arid environments, and we can see those salt deposits associated with these hot, dry environments with not much rain. And so we'd expect to find these huge salt deposits. We have different reefs associated with some of those more tropical environments. And so we can see that these continents fit very, very, very well together. We have places like Antarctica that are covered by glaciers. And if we take a look at this area, we can see on occasion, we find what are called glacial striations or grooves that show which direction the glaciers move. And so in South Africa, we have glaciers looking like they're going from the ocean to the land. And that wouldn't make much sense that ice moves uphill. But if we put Antarctica back in place, we can see that ice is moving from Antarctica to Africa. It makes a lot more sense. So Alfred Wegener had some really good evidence, but he had a lot of critics. More on that in just a second. So when we start looking at these other piece of evidence, one last thing that he looked at was different fossils. And if we start looking at these fossils, we have the same organism on two continents that are separated by a giant ocean. So how can you end up with the same species on two different parts of the world? Well, Alfred Wegener's hypothesis is they must have been connected. And again, it substantiates his hypothesis. Later, it was found that we started looking at the different mountain belts. And this also matched up. If we take a look at the Adirondack Mountains in the United States and the Africa, the Atlas Mountains and the British Isles, and we can see a mountain range extending all the way up through this entire region. We're going to learn this chapter that mountain ranges like these are caused from continents getting smashed together. So we have evidence in this area that there was the same forces pushing together, creating those same forces causing those same mountain belts. They're really one mountain belt that's been pulled apart. So I mentioned he had Alfred Wegener had a lot of critics. First off, they were the Geological Society at large. They did not like that a meteorologist was telling the geologists how the geology works. And so they had a number of different arguments, even taking to the point of going to Alfred Wegener's presentations and having people literally yell and taunt at him. And so, the last laugh goes with Alfred Wegener, who realized that his idea did stand the test of time. And as we collected more data, we realized Alfred Wegener really was onto something. So Alfred Wegener's biggest critic stated, we don't see the continents moving, and what kind of force is going to cause these continents to get pulled apart? How are these continents, what is the energy source that is going to cause these continents to move? Is it the And so Alfred Wegener looked at a lot of different things. He thought maybe the moon's gravitational pull, or the fact that the Earth is spinning on its side, and if it's spinning, maybe areas that are mountainous are going to hold back a little bit more. Unfortunately, he never found out what the cause of this force was. The critics said that the only way that the continents could, or you could in fact have these land bridges where organisms could in fact meet and interact and interbreed. And then we all know that weathering is going to wash materials away. And so those areas must have just washed away. So now we have much more evidence. After World War II, we had some very advancements in military technology that led us to being able to measure things very, very precisely. In particular, we were able to use a laser, a light beam, and having a couple of mirrors to account for the curvature of the Earth. And we could actually send a reflector and pass that light from the United States across to Great Britain and then back again, and we can actually measure the distance using the speed of light and do that same measurement the next year and realize it got further and further and further and further away. So that's one new technology that was developed, and it confirmed that Alfred Wegener was right. The continents were moving. And I mentioned Harry Hess identified that the ocean floor was not a perfect flat bottomless abyss, but in fact it had some some mountain ranges. And so here is a map of the ocean floor, in particular talking about a number of different ocean features. Now in chapter, the oceanography chapter, we have a number, we're going to talk a lot more detail about some of these interesting features that we're going to be pointing out. I do want to talk about, here's that continental shelf I mentioned where we transition from continental crust to oceanic crust, and you can see there's quite a distinct difference between the two. So we've got the continental shelf, which is just the submerged portion of the continent. We do have some flat areas, the abyssal plain, but it's not exclusively abyssal plain. We have this mid-ocean ridge system, and if we see this mid-ocean ridge extends, it splits apart, it goes across in through all oceans, so we would have to explain, plate tectonics would have to explain these ridge systems. Additionally, I mentioned there's some areas that are very, very deep. Here is the Mariana Islands, and we have Marianas Trench associated with that one. It's the deepest. Marianas Deep is in Marianas Trench, which is the deepest portion of this trench. But we can see these trenches off the coast of South America and to the east of Asia. So we'll talk about these trenches and why these trenches exist. One other piece of evidence that really, really helped us understand plate tectonics was the discovery of the epicenter of various earthquakes. And you can see when we start mapping out where these epicenters are, there is definitely trend lines associated with these earthquakes. Now we're going to talk more about earthquakes in chapter 8, so sit tight and wait on those earthquakes, but we can clearly see that there is a distinct boundary between where the earthquakes occur, and we're going to learn that that's where those plates are. So here is a video of the breakup of Pangaea. Mentioned Alfred Wegener came up with this idea of Pangaea. The word pan means all, Gaia, land, and so that's where that word comes from. So
Wegener proposed that continents were once all connected to form a vast supercontinent named Pangaea. He suggested that Pangaea broke up and that continents have been drifting apart ever since. In the centuries since Wegener, geologists have learned that Pangaea is only one of several supercontinents that have formed and that have broken up and dispersed during the past few billion years of Earth history. Supercontinents form when subduction consumes an ocean basin and the continents that were once on opposite sides of the ocean collide. Supercontinent breakup happens when rifting splits apart a continent. Then seafloor spreading produces new ocean lithosphere, so continents on either side can move apart. Let's look in more detail at Pangaea's formation and dispersal. Pangaea came into existence at the end of the Paleozoic when Laurentia, a landmass composed of North America and Greenland, collided with Gondwana, a landmass containing Africa and South America. Structures such as the regional scale folds visible in the Appalachian Mountains of the eastern United States are relics of this collision. A dinosaur living in early Mesozoic could have walked from Canada to South Africa in Pangaea. In the Triassic, narrow continental rift basins began to develop in Pangaea as the supercontinent began to stretch apart. Beginning in the Jurassic, however, around 200 million years ago, Pangaea began to break apart. Rifts formed along what is now the east coast of North America, and when rifting succeeded, the northern part of the Mid-Atlantic Ridge became established, and the North Atlantic started to grow. Eventually, South America split away from Africa, and the South Atlantic started to grow. In the meantime, complex plate geometries developed in the region between North America and South America, yielding the Caribbean Sea. Note that at various times, portions of the interiors of the continents were flooded by shallow seas. Now, let's look at the last 100 million years of this process by focusing our attention on the seafloor itself. In this animation, different colors represent the age of the seafloor. The blue represents the oldest, and the red is the youngest. The widths of the color bands represent the rate of seafloor spreading. Where the bands are wider, spreading is happening faster. The bands are widest in the southern part of the South Atlantic because this is where the fastest spreading rate along the Mid-Atlantic Ridge is taking place. Notice how the oldest ocean floor lies along the sides of the Atlantic Ocean, while the youngest occurs along the mid-Atlantic ridge. On average, seafloor spreading in the central North Atlantic happens at about 3 centimeters per year. At this rate, the ocean basin is getting wider at a rate of about 3 kilometers per million years, or put another way, 3,000 kilometers per 100 million years. This rate is therefore compatible with the concept that the ocean started to form about 200 million years ago, because it's now 6,000 kilometers across.
So as Harry Hess in shortly after World War II was able to identify, is that we have a mid-ocean ridge, and at that ridge, new crust is being formed in this area. And that crust is going to be moving further and further and further away from the ridge. Where we have old crust, what's going to happen is that old crust is cooler and more dense. And as a result, that old crust is going to get subducted. These little stars indicate earthquakes. You'll note that the stars are getting lower, and we can actually track where the plate boundary is based on what's called the Benioff zone, where these different stars or epicenter, where the focus of those earthquakes occur. And so eventually that descending plate will have enough water in here. It'll allow for additional volcanoes. And so we'll see a mountain range right where the plate is descending. This is why we have those very deep trenches. We mentioned off the coast of the Mariana Islands, off the coast of Japan, as well as off the coast of South America. Now, is a refresher from last chapter, we mentioned that that we have the crust and the mantle, but we could also break down the Earth into two major categories: the lithosphere and the asthenosphere. The lithosphere is these plates. So whenever I'm referring to a plate, I'm really meaning a piece of the lithosphere. Beneath the lithosphere is this asthenosphere. This asthenosphere literally means weak sphere. It's, I think I mentioned it's this warm, taffy, warm Tootsie Roll sort of material. It is relatively soft, able to flow, still technically qualifies as a solid, as S waves will travel through this material, S waves from an earthquake. And so the Earth is made up into about 20 large plates. There's a bunch of microplates as well. Just think if you dropped a hard-boiled egg, you're going to have some big shells, some little shells. The big difference between my analogy of an eggshell is that these plates will push towards one another, pull apart, and slide past one another. And so when we start looking at earthquakes, if we have a line of earthquakes, that's a really good indicator that we have an area that is going to have a plate boundary on it. And so if we're trying to identify where the plate boundary is, look for earthquakes. Once we've established where those earthquakes are, we can then identify where the rest of those earthquakes are, create that plate boundary, find the edges of that boundary, so we can identify this entire plate. And some plates that we're going to be focusing on is the Pacific plate, the North American plate. And I kind of want to talk about the North American plate because a plate can have continental crust and oceanic crust on the same plate. And so that North American plate extends all the way to the middle of the Atlantic Ocean, all the way out to the western edge of California, with the exception of this little sliver of California here that is in fact on the Pacific plate. We can have plates that are almost exclusively in the ocean, and this would be an example would be the Philippine plate or the Nazca plate here, or this little tiny plate called the San Juan de Fuca plate. And these plates can either pull apart to diverge, come together, converge, or slide past one another, transform. And so when plates are pulling apart, what's going to happen is these plates are moving further and further apart, and new material is coming up in between. If this occurs in the ocean, it's going to create a new ridge, a spreading ridge. But this can occur underneath the continents. We've got some famous examples of this where the plates are pulling apart and allowing volcanoes to occur. And one of the areas that this is occurring in currently is in Eastern Africa, in the East African Rift Zone. It's called the Rift Zone because this area is pulling apart. So when we start looking at current understanding of plate tectonics, again, we now know what the force is. So we are one step above the knowledge that Alfred Wegener had. And so we have this plate, this rigid lithosphere that's broken up into individual plates. These plates are underneath the plate is the asthenosphere. Underneath that lithosphere is the asthenosphere. And those plates vary in thickness that correspond with the continental crust. Where we have thicker continental crust, as you would expect, you'd have a thicker lithosphere. And underneath the lithosphere is that asthenosphere. Now, it's very, very interesting what happens when these plates move in relationship to one another. Movements don't, in fact, drift. That's a misnaming at this point, a misnomer, because they don't just drift. There has to be some force pushing them, pulling them, and we'll get into that today. So looking at the ocean floor, we can see that in all ocean floors, we have a mid-ocean ridge system. It's one ridge system that's connecting all of the oceans. And in the middle of that ridge is where new crust is being formed. And so here's a profile of that same cutout showing where that ridge is occurring. And so if I wanted to find some evidence of this, I would look for the age of these rocks to be younger than the age of the rocks closer to the shoreline. I get students asking, why is it so much higher in this region? A couple of reasons. One is as material is rising up, it's causing the crust to rise up a little bit. And what's going to happen as you move further away, it's going to cool off. When things cool off, they shrink a little bit. And so what we're going to end up with is these really flat areas called the abyssal plains, which were once part of the mid-ocean ridge that have since moved away. So magma rises up in the mid-ocean ridge, results in the spreading of the and formation of new crust. And then that material continues to move further away. So this is a time-lapse photo of these different, this ocean opening up. So as this material cools off, it will become more dense and sink a little bit into the asthenosphere. Additionally, further confirmation of this, besides just looking at the age of these rocks, we could also look at how much sediment. And the longer the plate has been around, the more sediment it would have on top of it. And so we can start measuring the sediment thickness. The further away from the ridge, the thicker the sediment. Now, when we get to the convergent plate boundaries, we really have to focus what is the type of material that is coming together. And so whenever we have an ocean plate that's being subducted, it's going to create a couple of different things, most notably a deep trench where the cool, older, more dense ocean crust is getting subducted underneath another plate. And whenever you have this cold plate being subducted, it's going to eventually get deep enough into the earth that it will start to give off some of its water. It will also, this friction is going to cause some additional heat into this environment, and it's going to allow some of that material to melt to create a series of volcanoes, whether it be ocean rocks going underneath other ocean rocks, creating a volcanic island, or it can go underneath a continent. And so since ocean rock is cooler and more dense, due to the iron content, that mafic rich materials, it's going to always be the one that is subducted. Whenever we have a continental crust and an ocean crust, the continent always wins. So again, looking at the earthquakes associated with convergent plate boundaries, we can track where that boundary is. Now, eventually what's going to happen is we'll get deep enough, and once we get beneath the lithosphere into that mantle, there's no pressure building up, and we'll end up with some more plastic flow. And as a result, we're not going to have any earthquakes deep enough into that asthenosphere. There's no pressure building up. Since this is capable of gradual flow, the pressures are going to move around it as opposed to stick and cause this very sudden movement, otherwise known as an earthquake. So when we start looking at continental convergent plate boundaries, we have some other types of convergent plate measurements. When we have an ocean and a continental plate colliding, I mentioned the continental crust is less dense, and so as a result, it's going to build up. Now, just as this ocean plate is being subducted, we still have our trench here. The additional material here is we have stuff washing off the continents, and any sediment that fell into the ocean is going to be less dense than that ocean iron-rich material, and so it's going to start to build up in this region. And this material here is called an accretionary prism, or exotic terrain, as is also a name for that is used in this area. And so we can see this just as if a bulldozer is just scraping along, piling up any sediment on top. Or if I were to step in a pile of mud and scrape my shoe underneath the table to try to get rid of all that extra mud, that would be a really good example of some of this accretionary material. And this can actually lead to the continent getting quite larger. So Harry Hess realized that if seafloor spreading is occurring and the Earth, if it was only seafloor spreading occurring, the Earth would get bigger and bigger and bigger. And we know that that's not the case. So if you're creating crust in one location, you must be destroying it in another. And so this is where we have this trench occurring. Now, the third type of plate boundary is called a transform plate boundary. And a transform plate boundary is where these plates are sliding past one another. Now, these are usually associated with the mid-ocean ridge as well. If we take a look at these two plates as a whole, this plate over here is moving to the left of the screen, and plate B is moving to the right of the screen. And so as these plates are pulling apart, they're not a clean, easy break. So we've got the ridge occurring right a little bit further on the right on the upper portion, and a little bit further to the left on the lower portion. And as a result, this area right in the middle will slide past one another. And there's earthquakes that will be occurring right in this region. But if we get further beyond either side of this transform plate boundary, these plates are moving in the same direction. Pressure is not going to build up, and you're not going to end up with earthquakes. This is also unique that this is one of the only type of plate boundary that's not going to be associated with volcanism, with volcanoes. And so we'll look at those as well, use that as an indicator. And so there's usually evidence where that scarring has occurred in the past, as in this region, but we can actually see the active fault is only in between the two portions of the mid-ocean ridge here. If we take a look at Southern California, we can see that the mid-ocean ridge extends into the Baja of California as well as into the Pacific Ocean. And so as a result, in between the two, we end up with this large transform fault. Probably the best example of this on the planet is the San Andreas Fault, which is, again, a transform fault. And so what that means is that San Francisco is on the North American continent, Los Angeles is on the Pacific plate. San Francisco is on the North American plate. And so the two plates are sliding past one another, and eventually Los Angeles is going to get closer to San Francisco. Now, as plates are colliding, what's going to happen is, again, continents never lose. And so they're always going to stay, they're more buoyant, they're always going to stay at a higher elevation. So when you have an ocean and a continental plate collide, eventually the plate that is being subducted, if it contains a continent, what's going to happen is those continents are going to collide and neither one is going to want to subduct. And as a result, it's going to build up. We're going to talk more about this in chapter 7, but some examples of this that have occurred in the past. One that's occurring are the Alps and the Appalachians, and one that's occurring right now is the Himalayan mountains. If we start pulling plates apart, this is again known as rifting. And some volcanic activity is very, very common in those regions. I do want to point out, this would be very similar to what's happening in Africa, where we can actually see some Mount Kilimanjaro is an example of this, where this rifting is occurring. And eventually what's going to happen is these plates are going to pull apart, and Africa is going to be split in two if it has enough force to continue. And so here's that African rift zone here. But it's not the only place. We have the basin and range region of the southwest part of the United States, and that plate is also rising up and pulling apart. And it's known as the Rio Grande Rift. Now, a little we are going to talk about this more in the chapter on earthquakes, but not in your book. We actually have a third kind of famous one in Southeast Missouri. At one time, we almost had oceanfront property here. Unfortunately, from my perspective, I would have liked to have an ocean. The North American continent almost pulled apart right here in Southeast Missouri, and it's known as the New Madrid seismic zone, or the New Madrid rifting that almost took place. So it's what we call a failed rift, and as a result, it had enough oomph to start pulling apart, but not enough to finish the job. And so as a result, what we're left with is just a weak spot in the continents. And again, we'll talk more about that in the chapter on earthquakes. There are some other unique locations on the planet, and this is where three plates will meet. Since these plates are moving throughout the continent, it's very, very common to get three plates meeting. What's unique about these plates is a lot of these are at almost exactly 120 degrees. And so when we start looking at these triple junctions, again, these are some very unique locations. we can see off the coast in the Indian Ocean, we have the Arctic plate pulling in this direction and this direction, the African plate pulling in this direction as a whole, and the Indian plate pulling in this direction. And so that's creating a very, very unique location there. We've got the San Juan de Fuca plate, a plate just west of the Cascade Mountain Range. We've got the San Juan de Fuca Trench here, and the Pacific Plate and North American Plate. And so in these examples, we have some more triple junctions. One other piece of evidence that really supports the idea, the theory of plate tectonics, is the use of hotspots. Now, we know that there are places in the asthenosphere that are really hot. These are called hotspots or mantle plumes, and they're stationary. And so as a plate is moving over them, what's going to happen is on occasion that heat is going to escape and we're going to be left with a volcanic island. And so what's going to happen is that island is going to no longer have that heat underneath it. And so the islands are going to be moving in a linear fashion. And again, some of the famous examples that we have in the United States are Hawaii, Yellowstone. It's not the only ones. We've got the Canary Islands, the Galapagos Islands are other examples of these volcanic tracts or isolated volcanoes, also called interplate volcanism, that occur as a result of these hotspots. Iceland is a very unique location because it sits on top of the mid-Atlantic ridge, and it's also at a hotspot. So we kind of get we get a double reason for volcanoes in the land of fire and ice in Iceland. One other piece of evidence that we'd like to use to support plate tectonics is the use of paleomagnetism, old magnetic signatures. And we know that if we have rocks that contain iron, as these igneous rocks cool off, they're going to point towards the North Pole, just like a compass would. And when the rock cools, the iron crystals can't move anymore, so their North Pole is locked in place. And if we start looking at the Earth's magnetic field, it's not uniform. It does, in fact, it moves over time. And so we've got a couple of different factors that we have to parse out what's moving and how does this relate to plate tectonics? Now, if we start looking at the iron crystals that are in different rocks in North America, it points to the red line here. And if we take a look at the rocks in Europe, it points to the yellow line, the dark yellow, light orange color. And so what happened is they're pointing to different spots. Well, we know North Poles always point to the same location. So here are some of the iron rich minerals. This is actually in between Fredericktown and Arcadia Valley. And you can see these little boring holes. They cooled off, or they used a cold drill and pulled out these little bits of iron crystals and looked at the orientation of those crystals. And they found that those rocks pointed to this spot. When we close up North America closer towards Europe, what happens is that those lines do in fact merge. And so we can see that here. Now, the magnetic fields do flip, where the North Pole will become the South Pole and the South Pole will become the North Pole. And that record is also in the ocean floor. we know that iron in the ocean floors, ocean rocks have more iron in them. They're what we call mafic. The F is for the ferrium or iron. And they lock in where the magnetic north is at any given time when they cool. Unless they are heated up to the Curie point, about 550 degrees Celsius, they will retain the orientation of those iron, where the North Pole was and when it had cooled. And so we can also use isometric dating, more on that in our chapter on radiometric dating, to figure out the age of those samples. And so then we can use the age of the samples and where the iron crystals are to determine what has happened on the ocean, how the ocean floor, or how the magnetic polarity of the Earth has shifted, has flipped. Here's a diagram showing these iron crystals here. With the work of Vine and Matthews, they went along the ocean floor and they would identify where the North Pole was at the various times in the past. And what it turns out, when they did a complete survey, they found that the magnetic field of the igneous rocks basically formed like stripes of a zebra parallel to the mid-ocean ridge. And so we can see the age of these samples as indicated here. So what is driving these plates? This is the information that Alfred Wegener really would have solidified his case. It has, in fact, changed over time. Alfred Wegener had no idea what the plan was, and I'm getting a little old now. The original idea was that we had these convection cells where heat is rising up and pulling apart these two plates, and it was a nice, pretty boundary. And when two plates were colliding, one of the plates was getting subducted at that portion of the convective flow. But as it turns out, we now know it's much more complex than that. There are two different mechanisms that facilitate this convective flow. Again, convection is moving up and down in a fluid, the two plates that are the two forces that we're looking at that are causing this pushing. The first one is the pushing factor, and where we have materials being pushed out, much like this water is getting pushed to the left of this screen on top of this force of honey. This material is moving away from the ridge, and that's pushing that material away. Additionally, at convection, at subduction zones, the ocean crust is much heavier and more dense, and as a result, this cold, dense material is pulling the rest of the material. Just like if I were to pull a tablecloth off of a table, the salt and pepper shaker that's sitting on the tablecloth would also go along for the ride. And so as I'm subducting that tablecloth, the material above it would go along. So those are the two mechanisms that are causing this flow. So lastly, we can look at how fast are these plates moving? Some plates are moving faster than others as a result of the different amounts of force. When we start looking at these plates, the red arrows indicate how fast these plates are moving relative to one another. So when we start looking at this area in the Pacific Ocean, we can see how fast this is moving away from this area. We now have the use of GPS, and we can actually put a pin in the ground and figure out its longitude and latitude. We can come back a year later and see what its new longitude and latitude is. If the plate has moved at all, we could actually track that in its velocity, and that's indicated here in its red arrows. Additionally, we can use the hot spot tracks. I mentioned Hawaii would be a good example of these hot spots, that we could actually look at the lava coming up, figure out how old that lava is and how far away from the hot spot it is. Anytime that we have a distance, and a time, we can calculate a rate. And as it turns out, these rates are all very, very consistent. I mentioned the GPS. And the average plate speed varies from 1 centimeter per year to 15 centimeters per year, which means that there are some areas that are moving faster than others, which means that pressure is going to build up. We could use this information to help us predict where we'd expect to see areas that are under a lot more stress than others. We could also look at this and figure out what has happened in the past. If we know that the plates are moving at about a couple centimeters per year over 200 million years, that's the width of the Atlantic Ocean. And so if we played this backwards, we'd see that those plates are coming closer together, and that's how we would end up with Pangaea. So as I'm going to go through these last class questions, if you have any questions, make sure you complete these quiz questions in MyMac. So make sure that you answer the questions.